Right. Throughout the textbook on kinematic synthesis, whenever you design something, whenever you synthesize a mechanism, you have to analyze. Now, for this, in GeoGebra, it is very simple. You use geometrical construction to analyze the mechanisms. In case of Excel, it is the same thing, but it has to be done analytically. So I will try to explain how you do it, and I'll try to explain how to use macro basic bus program in your computer to make life a little easier, let us say. So let me first share my screen. I will open an empty Excel sheet. I have several of these over here right now. So I will open a new sheet. Oh, yeah, here is the one. I only imported, I copy and paste. Using copy and paste, I inserted this drawing of a 4-bar and the necessary equations to explain you what I'm going to do. Now, this you can see in any mechanisms textbook, undergraduate mechanisms textbook. Whenever you have a 4-bar, you have a loop, a closed loop form. This closed loop can be solved using complex numbers, using vectors, and so on. The method that I'm going to explain is sometimes in some books called Reven's method. It is, I would call it stepwise method because it is an explicit derivation of the unknown variables using the known variables. But instead of obtaining a single equation for the input and output, you can do that as well using Freudenstein's equation and half-tangent form. Instead, I will explain a step-by-step procedure to determine the unknowns. Now, basically, we are given all the necessary link lengths for the analysis. In case of synthesis, we are going to determine those link lengths. But whenever you are given those link lengths, we form a quadrilateral. But you don't know exactly how this quadrilateral is because in case of a quadrilateral, this four-sided figure can collapse, can be at any position. So for determining this mechanism is going to have a 1 degree of freedom in that case. So we have to define one of the angles. It can be this angle theta 1, 2, which is the angular position of link 2 relative to this fixed link, or this angle theta 1, 4. In some rare cases, there are lots of cases, but not as much as these two. You can have theta 1, 3 defined. Now, if theta 1, 2 is given, I'll take that. That's the most common case. Theta 1, 4 given, you can analyze the same way as theta 1, 2 is given. When theta 1, 2 is given, you see, first, we have a triangle. We draw when you draw this diagonal, you don't have to draw it, but you have to imagine that there is a line drawn. We form a triangle. In this triangle, we know this side, the link lengths are given. We know this side, and this included angle. In that case, we can determine this length is B0A, and the angle this diagonal makes with respect to the horizontal axis, x-axis. So next, the basic idea is first you solve this triangle, and then next you solve the other triangle. Once you solve the first triangle, you know B0A, So you know this side, these three sides. So from side, using the cosine theorem, you can determine this angle psi and this angle mu, from which you can obtain theta 1,4 and theta 1,3. Now, in writing the equations, in determining this diagonal and so on, you have to use the vector concept. B0A is equal to B0A0 plus A0AA. Now, B0A is minus A1. A0A vector is this length I'll call A2. A2 cosine theta 1,2 I plus A2 sine theta 1,2 J in terms of Cartesian coordinates. So the x and y component of this diagonal is xs is equal to minus A1 plus A2 cosine theta 1,2. You see, A2 cosine theta 1,2 is in positive x direction. Minus A1 is in negative x direction. And y component is equal to A2 sine theta 1,2 here. Now, once you determine the Cartesian coordinates, determining s and phi is nothing but conversion of a Cartesian coordinate to polar coordinate. Now, s will be given by xs squared plus ys squared in square root, this length, A0, B0AE, and phi, this angle phi, will be given by inverse tangent y over x. Now, there's one gimmick though. If you write tangent inverse y over x, the computers do not understand whether y is negative or x is negative. So in that case, the output result is angle phi between minus pi over 2 plus pi over 2, first and fourth quadrants. You never obtain an angle in the second and third quarter. Now, in order to avoid this, what we do is we use double argument inverse tangent 2. Double argument inverse tangent. In your computers, in your programs, whether it is MathCAD, MATLAB, or whatever, it is inverse tangent is A10. Inverse tangent, double argument inverse tangent is A10-2. A10-2. In that case, you type x and y components separately, these two components. The computer will determine which x, whether x is negative or y is negative, and accordingly, you determine which coordinates this angle phi is. For example, in this case, it is in the second quadrant. In this case, x is negative, y is positive. But remember, in mechanisms, you see this shape, this figure for one position, whereas this mechanism is going to move, this crank A0A is going to move, rotate 360 degrees in most cases. So keep in mind, you can be in any one of the quadrants of the quadrants in any case. So whenever you are writing your equations, you must think about that. So this inverse tangent 2, double argument inverse tangent for phi is quite important. Then once you solve xs, ys, and then s, you can determine phi. And then this angle psi, you know s, you know A4, you know A3. Using cosine theorem and inverse cosine, you obtain the angle psi. This inverse cosine theorem will pop out quite often. Mu angle, this angle mu, again, using this triangle, inverse cosine, using the cosine theorem, arc cosine as such. Usually this idea is the product is the sum of the squares of the two adjacent sides minus the opposite side divided by 2 times the adjacent sides multiplied. That's very simple. Once you obtain these, psi and mu, you can determine theta 1,4 as phi minus psi according to this figure. However, in mechanisms, you can assemble this mechanism with the same link lengths with the other triangle, this ABB0, on the opposite side of the triangle. The two triangles are overlap. So in that case, it will be phi plus psi rather than phi minus psi. That's what we call cross form. This is what we call open form of a 4-bar. Thank God, when the mechanism is assembled in the open form, it will not go to the cross form. When it's assembled in the cross form, it will not go to the open form. So we are safe. So you have to take plus or minus once, and then that's it. Now, once you determine theta 1,4, theta 1,3 you can determine as follows. Extend this horizontal line from A. Now you have a triangle. The internal angles is, this angle is theta 1,3. This angle is mu, you know. Theta 1,3 you don't know. If you extend it, since the angle this side for this side is theta 1,4, the internal angle is pi minus theta 1,4. So the sum of the internal angles is equal to 180 degrees, from which you determine theta 1,3 is equal to theta 1,4 minus mu. Next, and the last thing we do is we determine a point C. Simply A0C, this vector, is equal to xc plus yc, xc I plus ycj, or xcyc. Now, that is equal to 2, is the sum of two vectors, A0A plus BC. Now, A0A, I know it is A2 cosine theta 1,2 plus, and I A2 sine theta 1,2 j. This vector BC, this length I must be given, B3, and this angle is a fixed angle I have to determine. Now, once I determine beta, or beta 3, I usually call it, in this figure it's beta. Once I determine this angle beta, AC vector is B3, this length, cosine theta 1,3 plus beta. Notice beta is a constant angle. Theta 1,3 is changing according to theta 1,2. Theta 1,3 is changing according to theta 1,3. And a B3 sine of theta 1,3 plus beta. So here is the result. Now, how do we implement this in Excel? This is an Excel sheet that I will be using. The first thing you have to do is insert the link lengths. What I will do is, over here, I will write A2, A1. First, I have to start with A1. That's simple. You see, I have to use subscript. I will mark 1 and call subscript. This you can turn on. You can have this subscript and superscript over the symbols over here by going to the Files Options menu and Customize ribbon. From the Customize ribbon, you select these indices and place it over here so that you can see. Or if you don't want to do that, what you can do is you can always and always do this. Mark 1, click format cell. Here it is subscript. Mark the subscript. Once you type A1, go over here, A1, A2, A3, A4. Okay? Now, let us make them central. I will also increase the size a little so that you can see. These are the link links that I will be using. A1, I will take 45, A2, 20, 55. Of course, you can change it. I'm just for the hell of it, and 30. For the length, B3 is equal to AC, that length. I will take 40, and for the length BC, I'll call it C3 is equal to BC. I'll take 50. Can you change it? Of course you can change it. These are the inputs. These are the given values. These parameters are link lengths. Now I have to have another parameter. This angle theta 1, 2. Theta 1, 2 is a running parameter. It is the motion characteristics. It is independent variable for the motion. So what I will do is, I will not write, these are constants. These are, for a given mechanism, these are given constants. Theta 1, 2, I'll type over here, like this. 1, 2, very easy. Now, in order to convert theta symbol, what I do is, now I mark theta, Q, come over here, determine the symbol, that's theta 1, 2. If you don't know which one, which Latin alphabet corresponds to the symbol, to a symbol, you simply come over here, say symbol, and start writing whatever you see on the board. And you will have all the Greek symbols available. Now, let me remind you something. Q is for theta, A is for alpha, B is for beta, phi, F is for phi, Y is for psi, and that's mostly what you will be using. Oh, I have gamma, G is for gamma. Okay, that's very simple. So let me erase these. Let us keep those. Now I will select a value for theta 1, 2. Theta 1, 2, let us say 22 degrees. I don't care. I mean, you will be changing it. I will be changing it as I go on. Now, first thing I will have to do is determine xs, ys, and s. So what I do is, row-wise, I will write these xs, ys, s, and phi. And then psi, and then mu. I think I'll keep it up to that point. Later I will continue, okay, like this. Since these are symbols, I'll come over here and make a symbol. And I have subscripts. Like this. Now, XS, I'm going to type the formula is equal to. Whenever you have to enter a formula, you have to write equal. Minus A1 plus, I'm not typing 45, mind you. I'm writing the name of the cell in which you have the length A1 plus A2 times cosine of, another problem. In all mathematical packages, in Excel as well, angles must be in radians. If you type theta 1, 2 in degrees, that's wrong. There are lots of different ways of doing this. First way is open up parentheses, type degrees, open up parentheses, this angle. Oh, I need another parenthesis. Now, let me show you this over here. I can type is equal to degrees, open up parentheses, this angle in degrees. Oh, I typed it wrong. That's the usual thing I do. Okay? Sorry, radians, I'm sorry. Radians. 11. That's type. Oh, sorry. I'm not using this, that's why I made a mistake. That's in radians. That's converting degrees to radians. I use radians. I can do another thing, and that is equal to 22 times pi over 180. If I multiply it, this angle in degrees by pi over 180, I will be converting it to radians. Now, either way is correct. There's no problem. But if you are going to do this over and over, if you are going to convert degrees to radians, radians to degrees, both methods are quite lengthy. I found out that there's a simpler way of doing it. You go to an empty place in your sheet, empty a cell that you think you will not be using. Over here, type pi over 180. Now, this factor can be used to convert degrees to radians or radians to degrees. If you multiply a degree with this number, it could be converted to radians. If you divide a number with this number, it will be converting radians to degrees. So what I do is, I give a name instead of O1, the name of the cell is O1. Instead of giving using that name O1, I mark here, and usually I type, I type D-R, like this. Degree to radian, that's something that I can remember. I do remember D-R, degree to radian. Now, once you do that, now you can convert 22 degrees to radians as is equal to this value times D-R. I found this simpler than any other way. So what I will do is erase up to here, open up parentheses, this angle times D-R. That's it. The same thing. YS, By the way, in some other cases, I will do this, depending on which one you use. Sometimes I do it like this. I type degrees, radians. I copy this. I multiply this value with d dash r, correct? Now, rather than typing dr all the time, I come over here and select the angle in gradients. That is sometimes very simple because, look, I will be using, if you look at these equations, I will be using theta 1, 2 here, here, and then I will be using theta 1, 2 here and here in 40 places. So rather than writing it 4 times, now I have it only once. Now, it depends, I mean, to your taste. Ys is equal to A2 times sine theta 1, 2 in radians, right? Now, S is equal to SQRT is the square root. It returns the square root of a number. Open up parentheses, XS, Control Shift 3, you will see nothing. Type 2, you will see the cap 2, that is squared, plus YS cap 2 squared, close the parentheses. That's the length. Angle phi equal to A tan 2. Remember, it returns the arctangent of the specified x and y coordinates in radians in between pi and pi, minus pi and pi. Open parentheses, xs, comma, ys. In some cases, if your computer is adjusted as such, it can be semicolon. Please check. In my case, for example, in my case, in my office that I'm using, it's comma. In my home, the laptop I'm using, it's a semicolon. I cannot say. I tried it, but I wasn't successful. This is the angle in radians. Please keep that in mind. If you want to see what angle that is, divide it by dr. That means it is 164 degrees when theta 1, 2 is 22 degrees. Psi, again, is equal to A cos, open up parentheses, another parentheses for the numerator, S squared, A4 squared minus A3 squared. Here is S squared plus A4 squared minus A3 squared, close parentheses, divided by, open up parentheses, 2 times S times A4. That's it. Close parentheses, close parentheses. For mu, again, I will use the cosine theorem. Only A cos A3 squared. If you don't place equal sign, it doesn't, it sees it as a literal. So to show that it's an operation, it's a mathematical function, I have to type equal. A3 squared plus A4 squared minus S squared, close parentheses, divided by 2 times A3 times A4, close parentheses, close parentheses. If you want to see these angles, all you have to do is, you don't have to type here. Take this cursor, it becomes plus sign, move it like this. This is relative cell addressing. So the formula is copied, and so the formula divides every term by dr. Dr is constant, so it is like that. Mu. Now, all I have to do is type theta 14, theta 13. What I will do is Control C, Control V, Control V. This is laziness, 4 and 3. Theta 14 is equal to pi minus psi. Pi minus psi. Theta 13 is equal to theta 14 minus mu. Let me repeat, this is for open form of the formula. These are the angles in degrees. Lastly, I have to determine this equation, but I don't have the angle beta. However, I have all the three sides of this triangle. So I come over here. Notice that is not a function of theta 1, 2. So I can calculate it over here. This rho is dynamic. When you change theta, it will change. But beta is a constant. So I will come over here, type beta V3. Make this symbol. Make this subscript is equal to A cos, open up parentheses, the two sides, A3 squared plus adjacent sides, B3 squared minus opposite side, C3 squared, close parentheses, divided by open parentheses, 2 times A3 times B3, close parentheses. That is beta 3. If you want to see it in degrees, this angle will divided by dr will give you the angle in degrees. Now you have beta 3, you have theta 1, 2, you have the link x, you know theta 1, 3. You can calculate xc and yc. Oh, this must be in times New Roman. xc is equal to A2 times cosine of theta 1, 2, keep in mind in radians, plus B3 times cosine of theta 1, 3 in radians, plus beta in radians. Yc is equal to A2 times sine theta 1, 2 in radians plus B3 times sine of theta 1, 3 plus beta 3 in radius. I have to written sim sine. That's it. We have completed the analysis of the formula. Now, let me show you something. Although I have done this calculation for theta 22 degrees, I can simply change it to 30 degrees. Right away, you can see that all the angles change. Oh, everything changes. If you want to see what happens when A2 is equal to 15, that's it. It is so fast, so easy to do. But usually the thing is, the problem is seeing numbers does not give me an insight of what kind of a 4-bar this is. I mean, I don't see anything. Oh, I don't see point C, and I don't see anything. It's just numbers. In engineering, we have to use some visual. We perform our calculations, that's fine, but we have to visualize what we have done. Only in that case we can understand whether we have made a mistake or not. Right now, I cannot tell you whether I have typed the function, the necessary functions correctly or not. So what I have to do is I have to visualize. Now, what I will do is I will first move these to one side. I'll keep the figure so that we can see. I don't have to see those formula. Now, in order to visualize this mechanism, all I have to do is draw lines between the joints. Then I can have a good idea about this mechanism, right? So what I will do is I will type A0, and then I will have A. If I draw a line between A0 and A, I will be able to animate the crank or simulate the crank. So A0 its coordinates is fixed. So it is 0, 0, 0, dash 0. This is the x coordinate, x and y coordinate. Of course, you can make it center. Let me make this center as well. A coordinate is going to be equal to, it is at a distance A2, making an angle theta 1, 2. I have to convert this polar form to Cartesian form to plot. So all I have to do is, equal to A2 times cosine of theta 1, 2. Keep in mind it has to be in radians. And equal to A2 times sine of theta 1, 2 in radians. Then I'm not going to start drawing. I'll first determine the points. Now, once I determine A0A, in order to draw this coupler link, notice I have to start from A, B, C, A, back to A. So what I will do, I have to determine B. C, coordinates of C, I have already determined over here. So what I will do is go somewhere in here. I can change this location. First, I will determine B0. The coordinates of B0 is fixed, a fixed point. It is at a distance A1 in x direction. So this distance is A1. And y coordinate is 0. B, coordinates of B, will be like this. Is equal to the coordinates of A. To that, I have to add this x component of this vector B0, B. It is A4, making an angle, theta 1, 4. Do I know the theta 1, 2 angle? Okay. I will simply do this. I have to see theta 1, 4, which is over here. That's why I did it. B4 plus A4 times cosine of theta 1, 4. That is the x component of the vector B0, B. The y component is again y coordinate of B0, which is 0, okay, fine, plus A4 times sine of theta 1, 4. The coordinates of C is equal to xc. YC I can move it, relative cell address. I have to, you see, if I start drawing a line from A to B to C, I have to go back to A to close that triangle. So I will type A, and this is equal to this vector. B, now over here, I will have, lastly, I have to draw B0, B. So I have B is equal to this value, which I have determined. That's it. Now, let me move this over here. I will insert chart in scattered points and straight line between the data points. Excel thinks it is clever, so it selects certain data accordingly. Okay, first of all, remove it, please. And then add x component. First, I will draw this line, A0A, and A0A y component. This line. This represents the crank. Okay, add A, B, C, A, which is that couplet triangle. A, B, C, A. This is the coupler. Okay, add B, B0, B, B0. That's your mechanism. However, there's something missing, and that is the scale, x and y scales must be the same. As you can see, from here to here is 10, from here to here is 10. They have to be the same. And secondly, if I do it like this, I change 30 degrees to 120 degrees, as you can see, all the scaling will change. In order to avoid these, let me do it like this. Mark this axis, format the axis. First of all, it has to be from minus 20. So I will change first to minus 20. This automatic should be reset. All those must be reset. This must be 60. Let me see. Yeah. Later, if necessary, I can change them. Make every measure grid 20 units. And then mark y-axis. Make, because it's a crank and it will be rotating 360 degrees, it has to be minus 20 at least. And upper row, I will make it 80. Later, if necessary, I can change these. Okay? Right. Now, let me close this. Now, it is 20 by 20. If I see those grid lines as a square, then I have the correct scaling, as you can see. almost a square. Sometimes I take a ruler and measure it from the screen on the screen. Nowadays we have flat screens, so you can do it quite well. The thing is, you can always change this angle, 210. Oh, as you can see, I have to change it. Format axis, let me make it minus 40. Okay. Again, I have to do it like this so that I see everything as these grids as a square. 220, 310. It works. Now, what I would like to obtain is, there are lots of things that I would like to do. As you can see, number one, by changing this theta 1, 2 angle, I can see the mechanism in any position. That means if I want to simulate it, I have to have some means to change this angle theta 1, 2 in steps. That I can do by going to the developer menu and using the insert buttons. If you're in your computer, if the developer menu is not turned on, go to the Files, Options menu, Customize ribbon, and mark this developer menu. Developer. That has to be turned on. Have a check on it. Now, once you have it, when you go to the design mode, you can use several different controls. I will use two of them. One is spin button. It has two-sided arrow, like this. Place it over here. Mark it, properties. What you can do is you can link this button to a cell in your on the sheet, and when you click it, it will change by a certain amount that you fix, that you set. Number one, this value, I will be assigning it to B11. It has to change from 0 to 360 degrees angle. It will be B11, correct? Now, small change, 1 degree at a time will be quite so slow, so I will take 5 degrees at a time, but it is to your taste. You can change the color of this button. You can do lots of other things, which I'm not going to discuss. If you want, you can, try it, shadow, all kinds of things you can do. Now, close the design mode. Now what you can do is, as you can see, it moves. If you don't want this, if you want to have a continuous rotation, in this case, it will be stopping like this and that. What I sometimes do is like this. Okay? The increments, I will take 5 increments in a degree increment over here. I will say, instead of go to the design mode, instead of attaching this button to B11, I'll attach it to A11. This time, I will change it from 0 to 1000, just for the hell of it, and I'll make it 1 unit. Okay? Now, when I move the design mode, as you can see, that's it. Now, what I will do is, I will type something like this. Mode, so first I have to say equal, mode, as you can see, mode, Is very, no, not this mode. There's remainder after number, mode. Open up parentheses. I will take this number multiplied by this number, comma 360. Now, what this does is, it takes whatever you have at BA11, multiplies by this step, 5 degrees, and if it is greater than 360, it subtracts 360. If not, it will be the number. It is the remainder after you have divided it by 360. So that's it. Now look. It will have a continuous rotation. When it goes to 360, let me show it. First 0, as you can see, it's very quite fast. 0, 72, this is 72, 2, this is 5. The step back, 355. So this number for theta 1, 2 is going to change from 0 to 360, that's correct. And if you want, instead of 5, you can type 2. It's going to change by 2 degrees interval. You can type 6. It's going to change by a 6-degree interval. Okay, that's a simple trick. And another thing is, go to the design mode. Take the scroll bar. The scroll bar, some people like it more than this spin button. I like the spin button myself. Now, go to the properties. Again, this linked cell will be B11. Okay. It's going to change from 0 to 360. Make it 5 units. Now, close the design mode. You can change it like this. Whichever you like. Well, you can do it. Now you cannot do it. So you have to write the formula in. Mode. Okay. Now this is in effect. Okay. I mean, don't use both of them in this case because the formula is eliminated when you use the scroll bar. Once you have simulated the mechanism, of course you can change the colors, etc., etc., etc. I'm not going to discuss all those because it takes too much time. You have to, of course, you can, make it look much, much better than before. Okay, like this. But I would like to see how this path is. The thing is, in order to see the coupler path, I have to draw this to determine this coordinates of point C for every degree as for of theta 1, 2, every theta 1, 2 angle. in a certain step. If you want to be more accurate, you have to take more steps. If you want to just arbitrarily, you can take less steps. If I take 5-degree increments, I will have 72 points, and I can draw a smooth curve between those 72 points to see the coupler path. Now, in order to draw them together, I know every point xc, yc over here, but this xc, yc corresponds to 1. I have to know all of them at the same time. So what I can do is I can write over here, take theta 1, 2, Control C, Control V. Let me take this angle as well, Control C, Control V. No, I will take the under 26 degrees. What I have to do is I have to copy this row in which I have the algorithm to any other row. In such a case, I have to keep the link lengths fixed, but change theta 1, 2 for each row. Okay? The link lengths for each row must be fixed, but theta 1, 2 for each row will depend on what you type on column B. Now, if I copy these formulas, Control C, Control V, notice except the radian term, all these formulas give me a wrong result. What's the reason? And why do we have radians correct, whereas the others wrong? In case of radians, notice B19 is what I want over here. That's correct. And DR is a fixed cell address. It's a fixed cell address. Whereas over here, theta 1, 3, okay, theta 1, 3, excess. If you look at the formula, C11 corresponds to theta 1, 2, which I wanted to change. B1, B2 are absolute cell addresses. These are the link lengths. Now, when I move this formula over here, I want to have C11 changed to C19, this value. Whereas B1 and B2, I must keep fixed. However, when I move this cell over here, notice B1 and B2 has converted to B9 and B10. The reason is, in Excel, the cell addresses given by Excel itself are what we call relative cell addresses. The distance between the formula cell and the cells that you are referring to have a certain distance in terms of column number, number of columns, number of rows. That number of columns and rows remains the same when you have the formula. So what happens is the rows and columns from B1 to B1, B2 changes to B9, B10. Whereas you don't want that. You want C11 to change to, C19, but B1 and B2 you want to keep fixed. That you can do in two ways. In one way, you can give names to those cells. As I have done for DR, I can give names to A1, A2, A3, A4. Sometimes it's useful, but if you have too many of those names, it starts to be confusing. You have too many names. Instead, use the name given by Excel, but make it fixed cell. fixed cell address, absolute cell address. So what you do is go to the right of B1, type F4. Go to the right of B2, type F4. Don't type F4 to C11 because you want C11 to be relative cell address. You want B1 and B2 to be absolute cell address. Now, if you take this, Control C, Control V, notice it is the same for other 26 degrees. Similarly, make B2 absolute cell address. S, D11 and E11 should be relative. D11 and E11 should be relative. In this case, F11 should be relative, corresponding to this row. B4 must be absolute cell address, B3 must be absolute cell address, and B4 over here must be absolute cell address. Similarly, over here, B3 must be absolute cell address, B4 absolute, F11 no, B3, B4. Now, theta 1, 2, theta 1, 3, 1, 4, XC, B2 must be absolute cell address, E1 must be absolute, E3 must be absolute. Notice C11, K11 is not. They shall be relative. B2, absolute, E1, absolute, E3, F1. Now, notice, if I copy these cells now, Control C, Control V, look, I have the same result. If I change this to 23 degrees, everything changes. Of course, if I change this to 20 degrees, or let me change it to 30 degrees, this 30 degrees, the same. So in this case, what I can do is now change theta 1 to 0, 5, 10, 15, 20. I think that's enough. First of all, make all these centered. Pull this down. Oh, too much. 360. Of course, you can make it every 1 degree, every 2 degrees, every whatever you like. But just to show you, I made it every 5 degrees. That's good enough. And then double click. You have all the cells filled in. Now, all you have to do is, let me do one other thing, show you one other thing in here as well. Move these XC, YC one cell up to make life a little easier for you. By the way, I have to change this to 80 to see that. As you can see, as I go on, as I see what's going on, I can change the coordinates, increase or decrease the scale, do whatever is needed. Now I want to plot this coupler curve, what we call. Go over here, select data, add. X coordinate will be the X coordinates of point C. Go to the first term of XC, Control Shift, and then press down arrow rather than scrolling up. Go to the last term of Y, Control Shift, up arrow. The reason why I have moved the heading one up is using this arrow. In that case, it stops at the empty cell. So that's what I have done. Now I can move this back. That's a simple thing. Now I will marker options. I will have none. This line I will have a solid line. The color, okay, let me make it red as well. As you can see, I have the coupler curve. The beauty of this is you can animate the mechanism, simulate the mechanism. And one other thing is you can ask, what happens if the crank length is 15 instead of 20? You can ask, what happens if the fixed link length is 50 instead of 20 or 45? What happens if 55 is 50? You can do all sorts of things, okay? You can change it. What happens if this is 25? As you can see, this is whatever you have done. This sheet is good enough to analyze the forward. The thing is, this 4-bar business, in this case, I have done it correct. If you want, you can plot theta 1,2 versus theta 1,4 versus theta 1,2, the transmission angle versus theta 1,2. But to do that, first of all, you have to change. What I do is usually I take these two, Control C, Control V, degrees. These are all in radians. This term divided by dr, open close parentheses. Sorry, not open close parentheses. I will show it later. dr. Now move it down. That's the transmission angle, the theta 1,4. Double click. You have theta mu and theta 1,4. Now go to Insert menu, turn on a new graphics, this time smooth curve. Select data. Where is the select data? Okay, here. Add first term, x, okay, I'll show it in another way. X component will be theta 1,2 all the way down. Mu, can you see it? It goes up. I want to stop it at 19. So 17 should be 19 in this case. That's what I should do. Okay. Add. If you don't empty that cell, you have to be careful. Make it 19. Okay. Okay. Let us see what we have. Oh, there's a sharp change in this curve. In mechanisms, you never ever will see a motion as such. Theta 1,4 changing abruptly like that. The reason for this is it goes to 100, let me see, 160 degrees and then jumps to 200 degrees. 200 minus 200 degrees, if I add 360, will it change anything? No. So if I add 360 to it, it will go up. So let us look at these values. As you can see, it moves 153, then on 250. To this, if I add plus 360 and for the rest of the terms. See what happens. Now, this is angle theta 1,4. Usually what I do is, let me show that as well. Mark one of the data points, add data label, go over here, mark on it, theta 1,4. Okay. Number one, enlarge it. Number two, take the Q, make it, oh, I don't have it, symbol. And then mark 1,4. Make it subscript. That is theta 1,4. You can move it anywhere you like. Come over here, whichever cell you want, whichever point you want. Add data label. And first enlarge it. Yeah. Of course, you can change the color. For example, right away, I will say change the axis type, from 0 to 360 and every 30 degrees. That's usually what I would do. Okay? That's it. Transmission angle, mu, and output link angle, or rocker angle, sometimes called. Now, from here, you can measure all sorts of things, etc., etc. Now, the thing is, in certain cases, I don't want to perform all this calculation over and over. I don't want to write all these formula each time. If it is just for the analysis as such, yes, you can do that. But what I can do is, you remember all these formula that we used? That I moved somewhere over here. Instead of typing all these formula again and again, or what I can do is I can place this in a macro, so that in one command function, I will be able to determine theta 1,4 and theta 1,3, or both. Okay, that will make my life easier. Another thing is, in most analysis, geometry, whenever you have to solve some geometrical problem, this cosine theorem we use very often. That's in plane. Cosine theorem is the term that is the theorem that we use most often in geometry. And another thing is conversion of Cartesian to polar coordinates. This formula we use quite often. Thank God we have a formula A10-2 function available in Excel, but there is now a function that will give me the magnitude of a vector whose x and y components I know. Or there's no formula that will give me the angle or magnitude using the cosine theorem. So what we can do is, we can type small programs for not just for 4-bar, for cosine theorem, for sine theorem, for cosine theorem, determine the magnitude, etc., etc. This I have already done. I open up a new sheet. In the first sheet, I have the 4-bar analysis that I have made. Now I have turned on in another sheet. I'm still in the same Excel file, book one. What I will do is I will import a number of macros into my Excel file. And the way we do it is go to the developer menu. Over here, you see Visual Basic. Here's the module for Visual Basic. This is the screen for Visual Basic. Right now, it is empty. You see the sheets, and I haven't done anything for that. So go to File, Import File. Over here, I have Basic, bus file. You can download this from the address that I have given in the book. Now, as you can see, I have a new module. These are very simple modules. Function 4-bar determines the output rocker angle with respect to the fixed length. Function 4-bar coupler. Function gives you the coupler angle, theta 1,3. Function 4-bar 2 gives you the angle, both of the angles, theta 1,3 and theta 1,4. Slider crank 2 gives, this slider crank gives the displacement of the slider. This slider crank 2 gives the displacement of the slider plus the coupler angle. Slider crank coupler. And the one that I will invert a slider, you have to check these formulas. You have to see what they do. I will show you, explain it in a minute. Function mag, these are the functions that I use very, very often. Mag is square root x squared plus y squared. That's it, mag. Write mag xy, it will return the magnitude. Ang xy, it will return, it is similar to A tan2, except A tan2 function will give you angles from minus 180 to plus 180. There's a certain, the break point is 180 degrees. Minus 180 to plus 180. There's a break point 180 degrees. Whereas in this case, the ang function will give you angles from 0 to 360 degrees. There is a break at 0 degrees. So in some cases, this is better than using the A tan2. These are the same concept that Excel has used. These two functions are the ones that I use very often. Function encos. It is very simple. It uses the cosine theorem, given the three sides, U2, U1, U2, and opposite. U1, U2 are the two adjacent sides. Opposite is the opposite side. That's it. It will give you the angle between the two adjacent sides, encos AA. This is the cosine theorem. All I have done is written the cosine theorem. Notice these are very simple programs, simple routines. Function mag cos, given the two sides, two adjacent sides, and given the angle, it will return the magnitude of the opposite side. That's it. These two functions in Excel, you only have a tan function. So in order to use a cos, a sin in Visual Basic, not in Excel. In Visual Basic, you only have a tan function, and it is written differently than in Excel itself. ATN is written. Whereas in case of Excel, it is an ATAN. So in here, you determine a sine and cosine functions. So you can use in other routines, macros, you use these sine and cosine functions, inverse sine and cosine functions. And I have written a function dr to convert radians to degrees to radians, sorry. These are very simple functions. So when you go to the sheet, for example, formula, insert function, you already, these are the functions that you already use. Here you have a user-defined function. Now, encos returns the angle in radians of a triangle whose three sides, u1, u2, and opposite are known. This angle is opposite to the side opposite. I think that's explanatory. Or, let me write 4-bar. It explains how you do it. Okay. Just. Now, let me show you something. Here, I have used these lengths. First, let me take these. Control-C. Control-V. Those are the link lengths. I'm simply copying them. And I will copy these. Control-C. Control-V. And Control-C. Control-V. I think I have it like this, so I can do it very easy. First, let me copy the figure itself so that you can see. Okay. Control-C. That's very easy. You see? Control-V. Now, I had to determine this angle based on 3 I called. Okay? Equal to. If you don't remember, you can go to the functions. But I remember. It is ang cos. As you can see, I can type it. Open up parentheses. The adjacent sides, A3 and B3. A3, comma, B3, comma. Opposite side is A3, C3. Close the parentheses. I think you can see that it is much easier, much faster than typing that ANCOS formula, ACOS formula. You know, using it is the cosine theorem. Now, let me notice the same angle. Now, let me take theta 1 to 140 degrees, 150 degrees. Control-C. That's all I will do. Over here, I'll write. What was it? Sorry, 150 degrees, right? 150 degrees. Now, what I will do is I will mark 2 cells. First, let me do that. Go to the formula, go to the function menu, go down, click 4-bar 2, returns both the coupler angle and the rocker angle when the link length and the crank angle is given. All my angles must be given in radians. Config is +1 if the mechanism is assembled in the open form, -1 if they're assembled cross form. Click OK. Crank. Press F4. Coupler. A3. Press F4. Rocker. A4 plus F4. Press F4. Fixed. 50. F4. Config, as I said before, it has to be +1 in this case. Theta in radians, keep in mind, this is in degrees, times d-r, open, close, this time I will use open, close parentheses. Oh, dr is available, so it takes dr. Okay? I have both right now, so that's why when it is dr, it's correct. Now, one difference, since you have 2 outputs, you have to press Control Shift and then enter. Now, the first term is theta 1,3. The second term is theta 1,4. Let me copy these and show you that Control C for 150 degrees. 150 degrees, right? Place numbers. Notice in here I have theta 1,4, theta 1,3. Theta 1,3 is, as you can see, this term, let me make it color, is equal to this term. And this term is equal to this term. It can give you this result. Rather than writing all these formula, I have a single one equation that gives me, that solves the 4-bar. If you are going to analyze the function, a function routine, usually what I do is, okay, now come over here, type theta 1,2, or instead copy this formula, Control C, Control V, 0, 5, 10, 15, let me see, yeah. Just for the hell of it, simply Control C, Control V, let me do it radians, degrees, as you can see, I can do it quite fast. Divided by dr. Okay, as you can see, I can do it like that. This is a very simple way of analyzing a mechanism. Of course, if you don't want to see theta 1,3, if you don't want to use theta 1,3, you can use 4-bar. Usually, what I will do is, for example, Control C. I will type over here, Control V. I will usually do it like this, Control C, Control V. Whenever I'm not interested in the coupler link motion, whenever I'm not interested in coupling point or coupler link motion, I type equal to 4-bar, open parentheses, A2, comma, A3, comma, A4, comma, A1, comma, 1, comma, this term times dr, close parentheses, enter. As you can see, I have theta 1,4 on there. Now what happened is I have an Excel in which I have special functions that my user-defined functions that I can analyze my mechanisms very fast. You see, in synthesis, whenever you design something, you have to analyze. Now you have this tool for every case. You can analyze your mechanisms very fast using this method. This is all that I'm going to talk about for the analysis. Okay, have a nice time.